Yeah, thank you very much for this kind introduction and welcome to my talk. It is really all about how can we really solve the challenge in characterizing the modern image sensors. This is really a challenge. Oops. And this is also a challenge here because it's not working. Yeah, the computer seems to be frozen. The computer seems to be frozen here. And here? Ah, now it works. Okay, so first challenge solved. Well, how can we really cover this large variety of modern image sensors? It starts, of course, with simple monochrome cameras, color, multispectral, hyperspectral, polarization. Then we have, if we need a higher dynamic range, we have nonlinear and high dynamic range cameras. We have finally cameras where the image quality is already enhanced. And so how can we do this one? We have time of flight distance sensing. We have so-called single photon avalanche diode SPAD image sensors. And finally, a completely new class, the event-based or neuromorphic sensors. And so what I would like to do is I will approach the central idea how we can have a simple and unified concept. I will quickly tell you what we need to measure and how we can measure that, and give you an idea of the rich EMVA 1288 toolset which is available. And then, of course, give you some examples that you see how this is all working. And at the end, I will, of course, also tell you where you can learn more. Okay, so the interesting thing is that you treat the camera as a system. And with this approach, you can cover almost all types of cameras. And to guide us how we have to set up the things, the first question we have to answer is, what limits actually the quality of an image sensor? And there are basically four things. The first thing is each measurement you do, you get a slightly different value. That is what we call temporal noise. That's this nasty thing that you never get the same. But with an image sensor, it's even more complex because you have not a single sensor, you have millions of them. And unfortunately, they are not all equal. So each of these pixels gives you a slightly different response, and that is what we call spatial non-uniformity. Third one is, even if you apply no light to your camera, you get a signal. And this signal is increasing with the exposure time you apply. So if the exposure time is increasing, you get a brighter and brighter image, and finally you can saturate your camera without any light reaching it. And so this limits basically the maximum possible exposure time you can use, and you need to analyze what is called the dark signal, how this is changing with the exposure time. Well, and finally, no sensor can detect unlimited light. It has a maximum signal that can be detected, and that is what we call saturation capacity. So these are the basic four limitations of image sensors. And how can we now get them? And the system theoretic approach, the power of it is that we do not know anything about what is in the camera. It's simply a completely black box. So we do simply an input-output relation. The input is the photons which hit the pixels during the exposure time. This gives us a mean number of photons. And this signal is already noisy because that is what is coming from quantum mechanics, that the variance is basically even to the mean number of photons you have. No camera manufacturer can avoid this noise. Then additional noise sources may be in the camera, and they influence then both the mean signal you get and also the variance of your signal. So this is always in mu, is a mean value, and in sigma, the correct sigma, you have the variance. And without any model and anything knowing in, what you still can do is you can do two important things. The first thing is you can measure the so-called sensitivity or characteristic curve. That means what is the signal I get as a function of the number of photons, basically from complete dark to saturation. The second thing what you can measure is, since you measure both your mean signal and the variance, you know the quality of your output signal actually. You know how good is actually my signal. And that is what we call the output signal to noise ratio. It's the mean value divided by the standard deviation then. And so the key parameter is really the signal to noise ratio. The definition is up here. It's of course the signal minus the dark signal, because you are only interested in light induced signal divided by the standard deviation. And the SNR is really the key parameter. The only trouble is, normally you think simply about SNR. But if you do not know the shape of the characteristic curve, if it's not linear, your input SNR might be different from the output SNR you are measuring. That is something you normally don't think about, because we are so much used to linear systems. So what we actually really want to know is not the signal to noise ratio at the output, but the signal to noise ratio at the input. That means the mean number of photons divided by the standard deviation, how good we can measure it. You are not interested really in DNs, you are interested in how bright is actually what I am measuring and how good can I measure this brightness. That is what you want to do. If you have of course a linear response, then things are easy. That is what we are used to. Then noise and signal is amplified by the same factor, and this input and the output signal are the same. If you have a nonlinear response, you can compute, fortunately, the input SNR from the output SNR by the slope of the characteristic curve. I cannot go into details. I just tell you we can do it, and at the end I will tell you where you can learn how to do it in detail. The next interesting thing is, you can always say what is the best possible camera. And the best possible camera is a camera where only the input noise is counted and no other noise sources come in. That means it is the standard deviation of the photon shot noise, and this is just a square root out of the mean thing. So the ideal SNR you can get is unfortunately not infinity, because you have a noisy input signal. It's just a square root out of the mean number of photons. That means you can always compare your camera with the ideal one. Then we have non-uniformity. You have them in the dark, that you get not only pixel to pixel variation, but unfortunately stripes like this. And the same is true, of course, for the sensitivity, that this might be changing, and even large-scale variations. And so the temporal variance actually is quite easy to learn, because we only need the variance. But for the spatial variance, it's more difficult. But still, we can measure these two things with only two images. That is another important key. One image contains, of course, temporal noise and spatial non-uniformity. You cannot distinguish it. But if you take two images and by the same conditions, subtract them, then you get rid of the spatial non-uniformity, because this is stationary. Everything what is not stationary is part of the noise. And so by taking the difference of two images, we have only in the difference image only the temporal noise. And then we can even go further. We can compute a column, and then we get only the row variation, because the column variation, of course, and the pixel to pixel variation is then basically eliminated, and we can also have a spatial, from the mean column, we can calculate the spatial row variance. So we can always distinguish non-uniformities, pixel variations, column variations, and row variations, which are very important for the non-uniformity. So we can put all these things together. We can also form a signal to non-uniformity ratio, which is basically the mean value divided by the standard deviation of the non-uniformity now. And if we put everything together, to the total SNR, it's a mean signal divided by the squared, by the sum of the variances, and then we have, of course, to take the square root out of it. So, and with the total, if we compare SNR and total SNR, we can immediately say, is a camera limited either by non-uniformities or by temporal noise? And measuring procedures is, I just tell you, of course, what we have to do is we have to take a sequence of irradiation steps from dark to saturation. Non-uniformity, unfortunately, we have to do many images because we have to suppress the temporal noise. There's no other way than averaging. So, but that we do only at selected, in the dark and at selected saturation, so only a few. And then we have to make, of course, a dark current measurement with a series of different exposure times. In addition, you can have optional measurements like temperature dependency of the dark current, or, of course, the dependency of the quantum efficiency as a function for the complete sensitivity range of the camera. And the nice thing is with the 1288 standard, you can always add, if a customer or yourself are interested in special properties, you can simply add them so that you get the information you can do. Of course, you have to do all the measurements at the same setting of the camera, because otherwise you can cheat. That is one of the important conditions that you have to do in these things. The irradiation is very flexible. We want to know about what is happening at the sensor, so we normally illuminate, as it's shown on the left, directly the sensor, but we can also do it with a lens, and we can also do it just with an aperture. So that you can, this is basically for the chief ray angle. You have sensors which have shifted micro lenses, and so with parallel illumination it would not work. So all these things are possible. And then we have a rich tool set, especially, of course, for the non-uniformities, because non-uniformity is not only characterized by the standard deviation. We have a statistical analysis, which is an overall evaluation, but then the really nasty things are patterns, because we, with our eye, sees it, and your algorithms also see it. Yeah, okay, a little bit closer. Okay, so we do then Fourier transform, so that you can see the really periodic patterns, and we do also that we can see the bad guys, so pixels which are outliers with a logarithmically scaled histogram, and we can capture basically all types of non-uniformities with a set of profiles, which basically give you a row, a mean row, and then positive outliers and negative outliers. But now let's finally come to the examples. The first thing are these profiles. The green line is a middle row. The black row is basically the black thing which you hardly see here, which is much smoother, is a mean row. So immediately you can see you have no column variation, because otherwise it would still, even in the average. So then we have the maximum values in each column. Then you see this is, of course, at the edge of the distribution, so it's shifted up, but you can nicely see you have 4 outliers, 4 so-called hot pixels. And then you can see for the negative outliers, it's suddenly almost 0. We have 1 line which is defect. So we saw then that the first line of the sensor was not okay. All these things you can immediately see with these profiles. A typical high-end linear industrial camera in the visible range. The most important thing is, of course, the SNR plot. This is the exposure in photons per pixel. And here we have the SNR, also in logarithmic scale. And then the thick black line here is the best possible performance you can have for a sensor without any improvement. And then you see the real data are a little bit lower. That is because of the limiting of quantum efficiency, which is not 1. So you have counting less. But then it's going parallel all the time, and only very much in the dark, the very dark, you see the influence of the dark noise. So not much dark noise is in there in this camera. And you see, the minimum you can see is where the SNR is 1, is about 4 photons. So the absolute sensitivity threshold is 4 photons. it's about, as you can see, the saturation range is more than 10,000, where the limit is. If you look now for a sphere camera, it's completely different. First, you have a much higher saturation because you have typically larger pixels. It's now not 10,000s, but it's 100,000s, more than 10 times. And therefore, although the highest SNR is not 100, but it's rather 400 here in this example, so 4 times better. But the curve here of the measurements is much steeper. That means over the whole range, this sensor is already limited by the dark noise. Completely different behavior. And that leads to a much worse absolute sensitivity threshold, which is now more than 200 photons. So you need more than 200 photons just to start seeing a signal. So you can nicely see how good it is. Then we have a final example, the HDR color camera, which is here now measured. You see all of them is a linear behavior. It's 24-bit signal. So a 1 million from 1 photon to basically more than 1 million of photons. And the SNR looks, of course, now different because there is switching between a large photodiode in the dark range to a small photodiode in the lower range and 2 different gains. So you see actually four parts in this curve. And finally, I show polarization. A sensor here, I just show you one thing, namely that we can have these nice histograms of the polarization angle. That's one of the tools in the standard. And you see nicely how well aligned this is with this sensor, that they are just changing less than 1 degree in the angle of the polarization. Very good behavior, and you see just one outlier here. That's really working very well. Well, and finally we may have a detailed analysis of the dark current because unfortunately there are these hot pixels, and here you can see there are a lot of pixels where the dark current is 10 or even 20 or 30 times higher. You have additional peaks here, and that is also something we have added in the new standard. So complete characterization of the camera, all you need for your practical applications. And let me switch the conclusions. Just further material, you can download all these slides. Let me just show you. Here I have, if you want to really do measurements, there are online courses. You can just grab one of these sheets here for the online courses. And I have also, that book just appeared a week ago, the new 8th edition digital image processing. Unfortunately, it's in German. But there is a detailed description also of the EMVA 1288 standard included in this book. So thank you very much for your attention, and grab one of these things if you are interested, or have a look here in the book. Thank you very much for your attention.